So the last video that we looked at dealt with how much material can be made if certain current flows for a certain amount of time. All of those problems work pretty similar. Look at the current you've got, look at the time that it passes, convert to seconds if you need to, and then into stoichiometry. The other kind of problem that is commonly encountered in a class like this is one like this. If you wish to generate (10.0 grams) of solid copper by electrolysis, again, it can be by electrolysis or by electrodeposition, whatever, in 1.50 hours, what current must flow into a copper sulfate aqueous solution in order to do this. So in the last problem, we knew time and current and calculated how many grams. Now we know how many grams we've got and a time, and we want to know what current needs to flow in order to do that. Well, in order to accomplish this problem, we need to know how many seconds this is. So 1.50 hours. And this is just the way I would solve the problem. There's probably other ways out there, but I know that I'm going to need this in seconds. So in this case, I'm going to convert it to seconds off to the side. Last problem, we did the seconds inside the unit conversions. 1.50 hours. There are 60 minutes in 1 hour. And 60 seconds in 1 minute. So we're going to get a number for this. 1.5 times 60 times 60. 5,400 seconds. Now the reason I got the time in seconds initially before we start setting up the rest of the problem is because while this one still uses unit conversions just like the last problem did, because it's a stoichiometry problem, and stoichiometry problems lend themselves to unit conversion setups, this one, we have 10 grams per 5,400 seconds. So I'm going to start this unit conversion problem with the unit conversion. We've seen this happen a couple of other times, but we're going to do 10.0 grams of Cu in or per 5,400 seconds. That's going to be our starting point on our unit conversions. It's CuSO4, that means it's copper 2 in solution. So our equation is Cu2 plus 2 electrons, making Cu as solid. That 2 we're going to need, just like we needed on our other example. We know how many electrons are being used up. So in some ways, we're working this problem backwards to the other one. We're going to go from grams of copper to moles of copper. So 1 mole of Cu, and on the periodic table, we've got 63.55 grams of copper. So now it's that many moles in 5,400 seconds, moles per second. Once we know how many moles of copper there are, we know that there's 2 moles of electrons per mole of copper. Two moles of electrons for every 1 mole of copper. Now we know how many moles of electrons. So now it's moles of electrons per second. We use our Faraday's constant. 1 mole of electrons in the bottom to 96,500 coulombs. Now we know coulombs per second. That's our units. And 1 amp is 1 coulomb. Sorry, 1 amp second is 1 coulomb. Coulombs cancel. Seconds cancel with our original seconds. Only unit left is the current that must flow. Okay. So now we calculate that one. So 10 divided by 5400 divided by 63.55 times 2 times 96500 equals 5.62 amps. So you'll have to pass 5.62 amps for an hour and a half to generate 10 grams of copper at the cathode for that process. So we're walking through each step that we did. I got the seconds by themselves because they were going to need to be in the denominator. 5,400 seconds for 10 grams of copper. Start out with a conversion factor there. Convert the numerator to moles of copper, moles of electrons, coulombs of charge, and then amps. Each step all the way across. All the problems set up like this one work this way. If you know the mass you're looking for and the time, it's going to be the same kind of process. Convert the time into seconds because you're going to need that for your steps along the way. Take your grams, convert to moles, moles of electrons, charge, and amps. All right. I hope this went okay for you guys. I know from past experience myself that electrochemistry is not always as straightforward to grasp. The delta G stuff is a lot easier because we did delta H last semester, so figuring out what delta G represents is not quite so difficult. Electrochem can be difficult, in part because you got terrorized last semester with those crazy acid-base redox reactions. Okay. Just take a deep breath as you do these. Remember that the more positive the potential is, the more spontaneous, the more negative, the more non-spontaneous it is. There's a relationship between delta G and K based on your E0 for your cell, or E cell if you're not at standard conditions, and go from there, okay? Thanks for paying attention, guys, and good luck.